Now, if V is an eigenvector, not necessarily unit of lambda I, which means AV is lambda I V, and V is not zero. Otherwise, it could not be an eigenvector. Then, how about QV? QV is AV V, therefore it is lambda I V V. So it is also lambda I V. The inner product of V and V is the norm square. So we have this useful result. We will use this later. And now we can classify all the symmetric metric according to the situation of their eigenvalues. So if lambda 1, the least eigenvalue, is positive, then the metric is called positive definite. And if the largest eigenvalue is negative, A is negative definite. Okay, and if lambda 1, lambda n is 0, that is the largest one or the smallest one is 0. So this means all the eigenvalues will not change sign. All of them are non-negative, or all of them are non-positive. So this case is called semi-definite. Okay, semi-definite, you can have a semi-positive definite or semi-negative definite. Okay, but this is not important. We will not discuss this in more detail. Finally, lambda 1, lambda n is negative. That is, you have positive and negative eigenvalues, then A is indefinite. Okay. Now we start discussing external value. Suppose omega is a subset of Rn and not necessarily opened, and A is an interior point of omega, and F is a function defined on omega. So this is omega, and this is A. So if there exists a delta positive, that is we want to say A is a local minimizer or local maximizer. That is, A is locally minimum or maximum. The precise description is that the value of F at A is the smallest one among all other points near A. So more precisely, if there exists a delta positive such that Fx is not less than Fa for x in the delta neighborhood of A. Okay, this precisely means that all the value of F at the point near A, Fa is the smallest one. But globally, maybe there are some point far away from A in omega, the value of F at that point is less than Fa. So Fa is locally minimum, but not globally. Okay, in omega. So in this case, we called a local minimizer of F. Okay, Fa is the local minimum. The value is local minimum. A itself is called local minimizer. Similarly, you can define a local maximizer and a local maximum. And also, the inequality here, you can replace by a strict inequality. So you have you get a strict local minimizer or strict local maximizer. Okay, so because the minimizer and the maximizer are important in some optimal problem, very useful. So it is important to determine which point is the local maximizer or local minimizer. We want to make the minimum or maximum value of the function. Okay, so in this respect, we have a famous and a very useful, important Feynman lemma. If A is an integral point of omega, I remind you that only for integral point we can talk about local minimizer or local maximizer, because you want to compare the value of f, which is the value of fa, the value of f at x and a. The x has to lies in the domain of definition of f, which means this ball must be contained in omega. So this implies A is an integral point. So if A is not an integral point, for example, A is here, for an arbitrarily small neighborhood of A, there are some part of this neighborhood outside the set omega. So fx there is not defined. So you could not compare fx and fa. So a necessary condition for a local maximizer or local minimizer is that A has to be an integral point of the domain of definition. So we assume that A is an integral point, and if this A is local minimizer for a function defined in omega, and also the partial derivative which with respect to xi of f at A exists. For some I don't require this to be true for every I. Okay, then this partial derivative must be 0. Okay, so this is the Feynman lemma. As a consequence, if the gradient of f at A exists, that is for every I the partial derivative exists, then every partial derivative is 0, therefore the gradient is 0. A point which 0 gradient is called a critical point. A is critical point of f. So this is the Feynman lemma. This part is my remark. The statement of the lemma is end here. Partial derivative with respect to xi is 0. Now we prove this lemma. This is a generalization of the one-dimensional case we learned in single variable calculus. Okay, so we draw a picture to help us. This is omega, and A is here. So A is an integral point, so there is a delta positive such that there is a delta positive such that the delta neighborhood of A is contained in omega. Okay, then we consider again we use our general idea to the multivariable function problem must be converted to single variable problem. So we restrict our multivariable function f to the xi direction. Okay, so we consider this function phi from minus delta to r. Phi t is f a plus t e I. Okay, this means we restrict f on this direction, on this segment, A is here. Then, because A is a local minimizer of A, we conclude that t equal to 0 is local minimizer of phi. Because t equal to 0 corresponding to A, other nearby t corresponding to some point near A. But Fa is the local, Fa is minimum among all points near A. So we see that for every t not equal to 0, phi t will not less than phi A. Therefore, t equal to 0 is a local minimizer of phi. So the derivative of phi at 0 is 0. But this derivative, by the definition of partial derivative, this is exactly the partial derivative of f at A. So this proves the lemma. Okay. Now, this Feynman lemma not only useful for finding minimizers for a function. To find a minimizer of a function defined in a domain, we only need to find a point where the gradient is 0, and the points where the function is not differentiable there, that is the partial derivative not exist. The maximizer and the minimizer must contain in all these points. So our range of search is narrow considerably, and the problem can be solved. Okay, so this is the application of Feynman theorem. But here we will show you another interesting application about the existence of a nonlinear algebraic equation. As I emphasized before, solving equation is a central topic, central problem in mathematics. So the first thing is that whether the equation has a solution. Okay, now we'll give an application. A is symmetric, positive, definite. N by N metric. Positive definite are only applied to symmetric metric. Therefore, A is symmetric. Okay, and F, capital F, is a C1 function in Rn. The close satisfies the inequality. For any x in Rn, this inequality is true, where C is positive and alpha is a number between 1 and 2. C and alpha are given. Given there is some C and alpha satisfies this condition, such that this inequality holds for all x in Rn. Okay, this condition, and we let f, small f is the gradient of capital F, which is a map from Rn to Rn. Because for x in Rn, fx is the gradient of f, which is a vector in Rn. So the gradient of f, of capital F, denoted by small f, is a map from Rn to Rn, and this map is continuous because the capital F is C1. The partial derivative of capital F, which are the component of small f, are continuous. Therefore, f is continuous. From capital F to be C1, we know that this small f is continuous. Now we consider this equation. Our conclusion is that Ax equal Fx is solvable. Solvable means that there exists a solution. There are some x such that Ax equal Fx. Solution exists. So this is a nonlinear algebraic equation.